before we discuss what directional derivatives and the gradient are doing, let's remember what the partial derivatives represent. So if we recall here, say if we have a function of two variables, z equals f of x, y, we know this defines some surface in 3D space. So maybe I can just kind of draw a surface here. Say we have something like this. Right. And we take a point on the surface, say x, y. Then, well, here, let me give us a coordinate system. We'll think of our coordinate system as described over here. Then what are the partial derivatives doing? Well, the partial derivatives are saying if you march a small distance in the x direction, what is the change in your surface? And the change in your surface in the x direction is the partial derivative with respect to x. So this is change in the x direction. Right? It's how is like there's a line or a curve we get here by holding y constant and taking just varying x along this kind of slice of the surface where y is constant. At your point, there's some tangent line here, and the slope of the tangent line indicates the change in the x direction. And that's what the partial derivative with respect to x was doing. And similarly, we had that partial derivative with respect to y is you hold x constant, look at the slope of the tangent line in the y direction where x is constant, and then this slope, partial derivative with respect to y, is change in the y direction. But you'll notice, because we are on a surface, there are an infinite number of directions that we could want to observe the change of the surface, right? Like, what if we wanted to look at, so let's say here we have some surface, right? And we want to look how this is changing at, say, like a pi over 4 angle from the positive x-axis. Maybe we want to see how the surface is changing in this direction instead of just the coordinate x and y directions. So the idea is that we want to define the change of the surface in any direction we choose based on theta. So if we took a line along this theta value that we would like, and we want to describe the change of what's going on, well, how you describe the slope of the tangent line here in this direction is first you start with we move a small distance. So let's say this is the point AB, right? And then you move a small distance, and we'll first get a slope of the secant line. The slope of the secant line between a point that we're starting at, so let's say a point that we're starting at, and then we're going to march a small distance here. So on the picture, it looks like it's far away, but imagine we're just like really zoomed in so that these points are pretty close together. Well, if this is the point AB, then notice we've marched in the x direction and in the y direction. And how much have we marched? Well, we've marched t cosine theta in the x direction, right? So let's say here that the linear distance here is just t. Let's say we've marched t units in the direction of some theta, right? Well, then we, in the x direction, you see we get a right triangle here formed with t being the hypotenuse, and then we have the height, or the height and the base of the triangle here. And what's the length of the base? Well, it's going to be a plus t cosine theta, and the length of the height is going to be a plus t sine theta. So the slope of the secant line here, which is the line traveling through these 2 points, is going to be, well, it's rise over run, right? And what's the rise? Well, the rise is a plus t cosine theta comma b plus t sine theta minus f of a b. That's the rise, right? Over the run, which is just h. So this gives us the slope of the secant line. And now if we take the limit as t goes to 0, then these points get arbitrarily close here. And we get the slope of the tangent line. And so we get the slope of the tangent line, which is also the definition of the directional derivative. So let me give a definition here. The directional derivative of f in the direction of u is, and we say d sub u f of a b, and then by definition, this is the limit as t goes to 0 of f of a plus t cosine theta b plus t sine theta minus f of a b. Sorry, that's a little scrunched. See if I can write smaller. F of a plus t cosine theta, comma b plus t sine theta minus f of a b all over t. And I said h here, which is, I want t. I think I was thinking about using h when we define partial derivatives. But just for now, I'll use t. And so this is the limit definition of a directional derivative. And for the record here, I should be a little more precise. What is u and what does it have to do with like theta here? We're looking at u to be a unit vector given by cosine of theta, sine theta. Okay, so the directional derivative, or how the surface or how the function is changing in a given direction, is defined to be the limit of the slope of the secant lines. Okay, and so just as it was with the derivative, single variable derivative, and partial derivatives, the limit definition is not fun when you actually have to calculate these directional derivatives. So let's see what we can do here to make this a little nicer in terms of how we can compute this. So I'm going to start by simplifying some notation here. So let me write x is a plus t cosine theta. And let me write y is b plus t sine theta. So that way our notation is just a little more concise. And next, imagine, so let's suppose we parameterize the function f of x, y. So what that means is we can write the function of x and y as a function of t, right? So let's say that f of x, y has some parameterization g of t. Well, then from the multivariable chain rule, if we want to take the derivative with respect to t, by the multivariable chain rule, we know that's going to be partial f, partial x, and then dx dt plus partial f, partial y, dy dt, right? This is by the chain rule. Now, when t equals 0, we want to look at g prime of 0. Well, if we look at when t equals 0, then g prime of 0 is just going to be, so let's look at what when t is 0, we can come back up here for a second. When t equals 0, what does that mean? That means x equals a, and it means y equals b. And so what what we have then is that plugging in, so I'll rewrite here, df dx, we're at the point a, b. And so this becomes f sub x, a, b. And now what's the derivative of x with respect to t? Well, it's just going to be cosine theta plus, and then something similar, right? We have df dy. But again, we're at the point a, b since t is equal to 0. So this is f sub y of AB. And then what's the derivative of y with respect to t? Well, it's sine theta, okay? And so let's keep in mind that g prime of 0 is this expression here. It's f sub x of AB times cosine theta plus f sub y of AB times sine theta. Now, let's compare this to the limit definition of g prime. So what's the limit definition? Whoops. Of g prime. Well, or how about g prime of 0? Well, the limit definition for g prime of 0 says this is going to be the limit as t goes to 0 of g of t minus g of 0 over t, right? But we know what g of t and what g of 0 is. G of t, we can substitute, g of t is just f of xy, right? And so that means we could just sub in f of xy and get the limit as t goes to 0 of f of, and I'll rewrite this now, getting rid of the x and y. So a plus t cosine theta, b plus t sine theta minus, and then what is g of 0? Well, if you plug in t equals 0, that's f of a b all over t. But this is exactly, if you'll notice, g prime of 0, this is the definition of the directional derivative. So we have that g prime of 0, this parameterization, observing g prime of 0 in the limit definition, we get that g prime of 0 is the directional derivative. Using the multivariable chain rule, we get that g prime of 0 is just this linear combination of partial derivatives and trig functions. And because of this observation, we can say that this is a formula for calculating the directional derivative. So, theorem. The directional derivative of f of xy in the direction of u, which is, again, cosine theta, sine theta, is, so we'll write d sub u f of xy equals the x partial derivative times cosine theta plus the y partial derivative times sine theta. And this is a much more convenient formula for calculating directional derivatives. And you can see it's just a linear combination of our x and our y partial derivatives. So it's taking the rate of change, like this formula we found for the directional derivative is taking the rate of change in the two coordinate directions, and then it's calculating rate of change as a linear combination of those, which is a lot easier than this limit definition here. So I think now would be a good a time as any to see an example of calculating a directional derivative. So let's let theta be arc cosine of 3/5. We want to find the directional derivative of, let's see, f of xy is going to be the function x squared minus xy plus 3y squared in the direction of u, which is, again, we'll just write cosine theta, sine theta. Okay? And so we need the directional derivative. Now, before we do anything, let's look at our formula. What do we need? We need, so when you have to find a directional derivative, usually what you do is say, what do we need? Okay, I need an x partial derivative, and I need a y partial derivative. Well, that's not too bad, now that we're pretty good at partial derivatives. So we can calculate f sub x to be 2x minus y, and we can calculate the y partial derivative to be negative x plus 6y. Okay? And then the next thing we need is we need cosine of theta and we need sine of theta. Right? We have theta equals arc cosine of 3/5. Well, for one, that tells us that cosine of theta is 3/5, right? Because arc cosine is the inverse cosine function, or it's inverse to cosine. And how are we supposed to then, so what we know is u equals 3/5, and then sine of arc cosine of 3/5, right? And so how do we find that? Well, we know cosine is what? It's adjacent over hypotenuse. So if we look at a right triangle here, triangle theta, it's adjacent over hypotenuse. And so the base of the triangle, or the adjacent side to the angle theta, is 3, and the hypotenuse is 5. Well, then that means, by the Pythagorean theorem, this is a 3, 4, 5 triangle, right? And so what we have then is that sine of theta is 4/5, right? Because sine of theta is opposite over hypotenuse. So we get that u is 3/5, 4/5, right? Because, again, we have now that sine of theta is opposite over hypotenuse, which is 4/5. Great. And so now the directional derivative of f in the direction of u is going to be, well, and then we can just 3/5 times partial derivative with respect to x plus 4/5 times the partial derivative with respect to y. And I guess we could clean this up a little bit here. We'll get 6/5 x minus 3/5 y minus 4/5 x plus 24, not 64, 24/5 y. And so I'll just save some room here. Looks like we're going to get 2/5 x and then plus 21/5 y. And so this is our directional derivative of the function in the direction of u. And so remember, this gives us a formula for calculating how the surface changes along this angle of theta equals arc cosine of 3/5. Awesome. So this gives a good construction and way of calculating the directional derivative along with an example. And there's, in particular, a very important directional derivative called the gradient. And so in the next video, we will be discussing the gradient and why it's so important and its applications.